One bad BGP decision can disrupt the internet. BGP directs traffic between networks, and wrong choices cause leaks and outages. Let's see how BGP works and why it matters. By the end, you'll know why BGP exists, how sessions form, what neighbor states mean, how attributes guide routing, how best path selection works, and how to configure and troubleshoot BGP. Interior routing protocols are built to move traffic inside a single autonomous system, but they are not designed for internet-scale routing between organizations where policy and inter-domain control matter. That's where BGP takes over. An autonomous system is a collection of IP networks under one technical administration presenting a common routing policy to the outside world. Think ISP, cloud provider, university, or large enterprise edge. At internet scale, shortest path alone is not enough. One network may prefer a paid transit provider, avoid a congested region, or refuse to carry routes for someone else's customer. So BGP was built around reachability plus policy. It lets autonomous systems advertise what they can reach, influence how traffic should flow, and make decisions without requiring one giant shared topology database. BGP is a path vector protocol. Instead of flooding the full topology map the way a link state protocol does, BGP advertises reachable destinations along with path information and attributes, so routers can make decisions based on policy, not just shortest visibility. The destination information is usually carried as NLRI, network layer reachability information. In plain language, that means prefixes a router says it can reach. BGP runs over TCP port 179. That matters because the session gets reliable transport, sequencing, and retransmission from TCP instead of reinventing that logic in the routing protocol itself. Once a session is up, BGP does not keep blasting the whole table every few seconds. It sends incremental updates when something changes, then uses keep alives to maintain the session. That design is one reason BGP can scale. Routers are not constantly recomputing a full map of the internet. They react to advertised changes and apply policy to what they learn. Another key idea is that BGP advertises reachability, not a universal shortest path metric. It can tell you who says a route is reachable and what attributes came with it. Then policy decides what wins. eBGP is used between different autonomous systems like enterprises or clouds. iBGP is used within the same autonomous system to maintain reachability without changing the AS number. Before we go deeper, lock in the mental model you'll use for the rest of the video. First, a BGP session forms, then routes are exchanged, then attributes are attached and compared. Then the best path is selected and installed into the routing table. If you keep that sequence in your head, the deeper mechanics stop feeling scattered and start fitting into one system. A BGP session does not appear just because two routers know each other's addresses. The peer IP has to be reachable, the autonomous system values have to align with expectation, and TCP port 1079 has to work end to end. Directly connected DBP neighbors might seem simple. However, issues like missing routes, ACLs, firewalls, wrong source interfaces, or TTL behavior can disrupt the session before BGP starts. For iBGP, loopbacks are often used as stable peering addresses, requiring underlying reachability through an IGP and the correct update source. BGP's finite state machine helps troubleshoot. Idle means the router waits for a TCP session. Connect is the next step, attempting a TCP handshake. Success leads to an open message. Failure means retrying. Active means the router retries after a failed connection, often due to reachability or TCP issues. If TCP is up and an open is sent, the session enters open sent, waiting for the other side's open to verify values. After valid open, the routers move to open confirm, expecting keep alive messages to keep the session up. Established is the goal, the session is up, updates can be exchanged, and the routers can now advertise prefixes and apply policy. Each state also hints at the likely fault domain. Idle can mean the session is administratively stopped. Connect and active usually point at transport or reachability. Open sent and open confirm often suggest parameter mismatch. Established with no useful routes means policy or advertisement issues. That is why strong BGP troubleshooting starts by asking not just whether the neighbor is up, but exactly which stage of the relationship is failing and what that stage depends on. Now we get to the point where BGP stops feeling abstract and starts becoming traceable. Once you understand the neighbor states and the message flow between peers, you can see exactly where a session is progressing, where it's stalling, and why. There are only 4 core message types, but they are the key to making BGP behavior predictable and troubleshootable. The open message starts the BGP conversation after TCP is up, carrying key parameters like the sender's autonomous system and BGP identifier. Capabilities show which address families and features can be understood in this session. UP-date messages handle routing. They advertise new prefixes, withdraw old ones, and include path attributes. If open is accepted, routers send keep alive messages to confirm the session is active. That means one update is not just saying this network exists. It is also saying here is the next hop, here is the AS path, and here is the AS signals that came with it. The last message type is notification. This is the session's hard stop. If a serious error occurs, a router sends a notification and resets the BGP session. Common causes include malformed messages, unsupported capabilities, ASN mismatch in some scenarios, hold timer expiry, or other protocol violations severe enough that the session cannot continue safely. Now tie this back to the state machine. Open sent is where open matters. Open confirm is where keep alive seals the relationship. Established is where update dominates normal operation. Notification can kick the session back down at any point if something goes badly wrong. Timers live underneath this whole exchange. The whole timer defines how long a peer can stay silent before the session is declared dead, and keep alives are sent often enough to prevent that silence under healthy conditions. So if you ever watch a session flap, think in messages. Did TCP fail before open? Did open negotiation fail? Did keep alive stop? Or did an update trigger a notification? That framing turns symptoms into likely causes. This is one of the big jumps from beginner to intermediate BGP skill. You stop memorizing message names and start seeing them as the protocol's actual life cycle. BGP path attributes are key to its policy. They enable BGP to steer routing decisions uniquely. A BGP route offers decision signals for comparing paths and controlling traffic flow. The destination piece is NLRI, the prefix information itself. The interpretation piece comes from path attributes, and that is where BGP becomes policy-driven instead of purely metric-driven. Attributes are also grouped by behavior, and that classification matters. Some are well known and must be recognized everywhere. Others are optional, and some of those are transitive, which means they can keep moving through the network even when every router doesn't fully act on them. The classic well-known mandatory attributes include origin, AS path, and next hop. If those sound basic, good. They are foundational because many later decisions depend on them. Next hop tells the router where traffic should actually be sent next. A route can look perfect in the BGP table but still fail to install or forward correctly if the next hop is unreachable in the routing table. AS path is the sequence of autonomous systems a route advertisement has traversed. It helps with loop prevention and also influences best path selection because a shorter AS path is often preferred by default. Origin is a smaller attribute but still exam relevant and operationally visible. Routes learned from IGP-originated network statement are typically preferred over incomplete origins when other earlier criteria tie. Local preference is one of the biggest real-world tools inside an autonomous system. Higher local preference wins, and it lets you say which exit path your own AS should prefer for outbound traffic. MED works differently. It is usually advertised to external neighbors as a hint about which entry point into your AS is preferred, so it is more about influencing inbound choices from adjacent ASs under certain conditions. Community is where BGP policy gets much more expressive. It tags routes with labels that downstream policy can match, like send this to peers, lower local preference, or do not advertise beyond a boundary. Weight is commonly discussed by Cisco learners, but remember it is vendor specific and local to the router. It never leaves the box, which makes it useful in labs and real tuning, but not a universal BGP attribute. Then there are attributes like atomic aggregator, which show up around summarization and route aggregation behavior. They matter less often day to day, but you should know why they appear. A powerful mental shortcut is this: some attributes help prevent loops, some affect how routes propagate, and some directly influence which path gets chosen. The same route advertisement can carry all three kinds of meaning at once. That is why advanced BGP work feels like reading a route's biography. You are not just asking where this prefix goes. You are asking who sent it, how it got here, what policy tagged it, and what decision those tags should trigger. This is one of the core payoff moments of the entire deep dive. Best path selection is where multiple candidate routes compete and the router chooses one through a structured sequence of comparisons. If you want to understand why one path wins and the others lose, this is the logic you have to know. It's central to real operations, and it's exactly the kind of reasoning you need for both exams and production networks. Best path selection is where BGP stops being abstract and starts feeling operational. A router may know several ways to reach the same prefix, but only one becomes the best path for installation and advertisement decisions. Before comparing attributes, remember one subtle point: the route usually must be valid in the first place, especially with a reachable next hop, or it may never make it into serious contention. Many certification tracks teach the sequence starting with weight. On Cisco platforms, higher weight wins, but because it is vendor specific, treat it as a platform rule rather than a universal law of BGP. Next comes local preference in the classic model. Higher local preference is preferred, and this is one of the main tools an AS uses to choose its own outbound exit point. If that still ties, locally originated routes are often preferred over learned routes. In other words, a router tends to like paths it created itself more than paths someone else handed to it. Then AS path length commonly enters the picture. Shorter is better by default because fewer autonomous systems usually means a simpler external path, though policy can absolutely override that preference. After that, origin type may be compared, with IGP generally preferred over EGP and incomplete in the traditional order. This is rarely the star of a design, but it still matters in tie scenarios and exams. MED can come next, depending on platform behavior and comparison rules. Lower MED is typically preferred, but MED handling is full of nuance, especially across different neighboring autonomous systems. If routes still tie, many implementations prefer ABGP over IBGP. That makes sense operationally because an externally learned route is often treated as more direct than one relayed internally. Then the router may compare IGP cost to the BGP next hop. Lower internal cost to reach that next hop can break the tie, which is why interior routing still matters deeply in BGP outcomes. Past that point, some classic tiebreakers include preferring the oldest path for stability, then the lowest router ID, and finally the lowest neighbor address if everything else is still identical. Here's the real-world nuance that keeps this honest. The exact best path order can vary by vendor, software release, enabled features, multipath settings, and address family. So learn the default sequence well, but don't mistake a default for a universal law. A good way to think about best path is in layers. First local overrides, then AS-wide policy, then external path characteristics, then internal reachability, then final tiebreakers. That layered model is more durable than memorizing a chant because when a route wins unexpectedly, you can ask which layer overrode the others instead of starting from zero. And if you are preparing for exams, do both. Know the expected order code, but also know where engineers in production start looking first, which is usually policy, next hop reachability, and whether the route was even eligible. Once you see best path as control comparison rather than magic, BGP feels far less intimidating because every winning route has a reason you can trace. That same traceable logic carries us into BGP design rules where topology starts to shape behavior. This is where route sharing, visibility, and attribute meaning get tied directly to how the autonomous system is built. The journey moves from protocol mechanics to architecture and scale. Here, eBGP and iBGP reveal the importance of BGP design in networks. Route reflectors, next hop behavior, and topology choices determine if the control plane scales well or causes issues. This is where the design layer matters. eBGP is simpler. Two autonomous systems connect and share reachability. iBGP allows routes learned at one edge to be shared within your AS without rewriting the AS identity. Now comes the famous iBGP rule. Routes learned from one iBGP peer are not advertised to another iBGP peer by default. This is often called the iBGP split horizon behavior. That rule helps prevent loops, but it creates a scaling problem. In a pure design, every iBGP speaker needs a session to every other iBGP speaker. Full mesh does not scale well as the network grows. Route reflectors solve that by allowing designated routers to reflect iBGP learned routes to clients. You reduce session count dramatically while accepting some additional path visibility and design considerations. Confederations attack the same scale problem differently. They break a large AS into smaller sub-autonomous systems internally while still presenting a single public AS to the outside world. You do not need to master every confederation detail on day one, but you should know why they exist. Large BGP systems need ways to scale policy distribution and path sharing without a giant full mesh everywhere. Next hop behavior is another major design point. In eBGP, the next hop is commonly updated as routes cross the AS boundary. In iBGP, the original next hop is often preserved unless policy changes it. That is why next hop self exists. It tells a router to advertise itself as the next hop to its iBGP peers, so those peers can actually forward traffic without needing direct reachability to some external address. You may also hear about synchronization in older BGP discussions. Historically, routers wanted to see external routes reflected in the IGP before trusting them broadly. Modern networks usually disable that behavior, but the history explains some legacy exam references. In an enterprise, a common pattern is edge routers running eBGP to providers and iBGP inward toward core or distribution routers. In service provider designs, route reflectors and larger policy frameworks become much more central. If there's one idea that changes how you understand BGP, it's this. BGP is fundamentally a policy engine, not just a route sharing protocol. That is what gives it power. It's how operators influence path choice, traffic flow, and routing behavior across real networks. Once you see BGP through that lens, the rest of the protocol starts to make a lot more sense. That means you do not simply accept every route and hope the defaults pick what you want. You shape what enters, what leaves, and how different routes are preferred. One of the simplest controls is prefix filtering. You can permit only approved routes, block overly specific or unauthorized advertisements, and prevent accidental leaks from spreading outward. Policy frameworks like route maps or policy statements let you match routes on conditions and then set attributes. That is where filtering turns into real traffic engineering. For outbound traffic, local preference is often your strongest high-level tool inside the AS. Raise it for routes learned from the exit you prefer, and your routers will usually choose that way out. For inbound traffic, things get trickier because you are trying to influence someone else's decision process. MED can help in some neighboring AS scenarios, but it is not a universal steering wheel. AS path prepending is another classic inbound influence technique. By making one path appear longer, you make it less attractive to external decision processes that compare AS path length. Communities scale this logic beautifully. Instead of writing custom policy for every prefix one by one, you tag routes and let upstream or internal policy react consistently to those tags. Next hop manipulation can also change where traffic actually flows, especially in more advanced internal designs. Just remember that changing the next hop without ensuring reachability creates broken paths, not elegant engineering. Here's a practical enterprise example. Imagine a company with two ISPs that wants ISP A to carry normal outbound internet traffic, while ISP B stays available as backup. Local preference can control the internal decision, while selective advertisement and AS path prepending can help shape how return traffic comes back from the outside. Another example is route leak prevention. You may accept a default route from a provider but absolutely refuse to advertise internal-only prefixes or unrelated transit paths back out. This is why strong BGP engineers always ask two separate questions. How do I want my traffic to leave? And how do I want outside traffic to arrive? Those are related, but they are not the same control problem. The difference between inbound and outbound influence is one of the most important BGP ideas to internalize early. It saves you from using the wrong attribute for the wrong objective. Once you see BGP as control policy expression instead of simple route sharing, configuration starts to feel much more logical. Every command is there to build a session, advertise a route, verify behavior, or manipulate policy. That's what carries us naturally into the configuration phase. Now the theory turns into implementation. This is where BGP becomes commands, session bring up, route advertisement, and the practical patterns you'd use in a lab or a real deployment. You're not just learning what the protocol means anymore, you're learning how to configure it correctly, bring peers up, and make the routing behavior match the design. When you configure BGP, start small and prove each layer before adding the next. A single healthy eBGP session teaches more than a huge lab pasted in all at once. In a Cisco-style workflow, you begin the BGP process with your local autonomous system number, then define a neighbor and the neighbor's remote autonomous system. That establishes the intended relationship. But that alone does not guarantee route exchange. The peer still has to be reachable, the session has to establish, and you need some method to originate or redistribute prefixes intentionally. The classic network statement advertises a prefix only when that exact prefix already exists in the local routing table. That catches many beginners because typing the command does not magically create reachability. So if a route is missing from BGP advertisements, one of the first questions is whether the matching route exists locally and matches the intended mask exactly. As the design grows, you may pair with loopback addresses for stability. That is where update source becomes essential, because the router needs to source the session from the address the peer expects. For eBGP across non-direct links, eBGP multi-hop may also be required so the TTL behavior matches the actual topology instead of assuming a directly connected neighbor. In iBGP, next hop self is one of the most commonly added commands because internal peers often cannot reach the original external next hop unless you deliberately rewrite it. Then come route policies. Prefix list, route maps, or equivalent policy frameworks let you filter what is accepted and what is sent, and they let you set attributes like local preference, MED, or communities. Modern platforms also support route refresh, which reduces the need for older soft reconfiguration methods in many cases. The big idea is that you can ask a peer to resend routes after policy changes without tearing the session down. If you are studying for certification, build the sequence in this order. Bring up the neighbor, originate one test prefix, verify receipt, add policy, re-verify, then scale the topology. That workflow matters because it isolates failure domains. If you dump neighbors, filters, communities, aggregation, and reflectors in at once, you lose the ability to tell which layer broke the result. So configuration is never just about syntax, it is about building the session, creating intentional advertisements, controlling attributes, and checking every assumption after each change. Once that habit is in place, verification commands stop feeling like a separate chapter and start feeling like part of configuration itself, because every BGP command should immediately lead to a check. Now we enter one of the most important operator skill sections in the video, verification. BGP outputs are not just walls of text, they are evidence. This is where you learn how to read session state, route details, and path information in a way that tells you whether BGP is actually healthy and whether those routes are truly usable. Verification starts with a rule that sounds simple but saves hours. Do not begin with the most detailed command. Begin with the command that tells you which layer is failing. A summary command is usually first. It quickly shows neighbor state, how many prefixes are received, and whether the session is established or stuck in a transitional state. If the summary looks wrong, move to the neighbor detail command. That is where you inspect timers, capabilities, message counters, reset reasons, and whether the peer relationship matches what you intended. Then inspect the BGP table itself. This tells you what routes BGP knows, which path is marked best, and what attributes each candidate path carries. After that, compare BGP knowledge with the actual routing table. A route can exist in BGP and still not install into the main routing table because of next hop issues, administrative distance, or better competing routes. Advertised routes and received routes views are invaluable when policy is involved. They help answer two different questions: what am I sending and what am I learning? On some platforms, received routes visibility depends on route refresh or soft reconfiguration features, so know what your device supports before assuming the absence of output means the absence of data. A strong verification pattern is this: session up, prefixes exchange, best path selected, next hop reachable, route installed, forwarding works. That order keeps you from chasing symptoms backward. If you are checking a policy change, verify both attribute values and route visibility before and after the policy point. A route map may match nothing, match too much, or set an attribute you are not actually comparing yet. For next hop issues, do not stay inside BGP commands only. Check the underlying routing table and reachability toward the next hop itself, because BGP can only use what the rest of the router can actually forward toward. The best engineers read outputs like a story. When did the session reset? What changed? Which prefixes disappeared? And which attribute caused a different winner? The commands are just evidence collection. That evidence-based approach becomes even more important in troubleshooting because most BGP failures are not random. They cluster into a handful of categories you can isolate systematically. Now we get to one of the most practical and valuable parts of mastering BGP troubleshooting. This is where you learn how to systematically isolate why a session is down, why routes are missing, or why the wrong path wins. Instead of guessing, we'll work layer by layer through reachability, session formation, route exchange, path selection, and route installation. That's how you troubleshoot BGP like an operator. Once that flow becomes habit, BGP stops feeling like a giant protocol and starts feeling like a sequence of testable assumptions. Troubleshooting BGP gets dramatically easier when you stop asking one giant question and start asking smaller ones in order. Is the session up? If yes, are routes being exchanged? If yes, are the right attributes present? If yes, is the best path installing and forwarding correctly? Start at reachability. Can the peer address be pinged or otherwise reached through the underlying network? If the transport path is broken, BGP has no chance to succeed on top of it. Next, confirm the neighbor definition itself. Wrong peer IP, wrong remote AS, or an update source mismatch can hold the session in earlier states long before route policy ever matters. For eBGP over non-direct links, check TTL behavior and whether eBGP multi-hop was configured as needed. For loopback-based sessions, check that both sides source and expect the same addresses. If authentication is used, mismatched passwords will break the session even when everything else looks right. The same goes for certain capability or address family negotiation mismatches. Once the session is established, shift your attention from transport to routing content. Are prefixes actually being originated, permitted, and advertised the way you think they are? A missing network statement, a route that is absent from the local routing table, or a disabled address family can all produce the same symptom, which is an established neighbor with missing routes. Route filtering mistakes are another huge category. A prefix list may block too much. A route map sequence may never match. A community-based policy may rely on tags that were never actually set. Then check next hop reachability. This is one of the most common reasons a route appears in BGP but fails to become usable. The path exists in the control plane, but forwarding has nowhere valid to go next. In IBGP designs, route reflection problems can also create confusing visibility gaps. A client may never learn a route because reflection rules or cluster design are not working the way you expect. Attribute and policy confusion often explains unexpected best path outcomes. Engineers may think Med should win when local preference already decided the result, or they may prepend AS path while wondering why their own outbound path did not change. That is why the reusable flow is so powerful. Verify transport, verify session state, verify route advertisement, verify policy and attributes, verify next hop, verify installation and forwarding. If you follow that order, most BGP issues collapse from a mysterious outage into a narrow class of faults, and each class points to a smaller set of likely commands and fixes. This is the mindset that matters more than anyone's syntax detail. The protocol is deep, but the diagnosis can stay structured if you keep isolating layers instead of guessing. Over time, that structure is what turns exam knowledge into operator skill, because you stop seeing BGP as a pile of commands and start seeing it as transport, policy, and path logic interacting in predictable ways. Now let's compress the whole deep dive back into one mental model you can actually carry forward. BGP forms a session, exchanges routes, attaches attributes, selects the best path, installs it into the routing table, then gives you the tools to verify and troubleshoot each step. If that sequence feels clear, the protocol stops feeling like a pile of separate topics and starts feeling like one coherent system. If you can explain why the session formed, why the route was advertised, why one path won, and why the next hop was reachable, you are already thinking about BGP the right way. That way of thinking scales from your first certification lab all the way into real multi-AS troubleshooting. If you are a beginner, work through this in order and make sure the foundation is solid before you chase edge cases. If you're further along, use this material to sharpen how you think about policy, path attributes, verification, and why one path wins over another. And if you're already operating at a higher level, use it to strengthen your design judgment, troubleshooting method, and control plane reasoning. We've covered why BGP exists, how sessions form, how routes are exchanged, how attributes drive decisions, how best path is selected, and how to configure, verify, and troubleshoot it in a real operational way. That's a serious working model of BGP, and it's the reason this deep dive matters. BGP quietly shapes internet path decisions every day. Now you have a much stronger framework for understanding how it behaves and how to work with it confidently. In the next few weeks, I am going to try and set up my lab where we will see BGP in action. So stay tuned.